first speaker doesn't need much introduction. Barnett Newman from Japan, Tohoku. Oh, Gerrit Bauer. And feel free to start, Gerrit, whenever you're ready. Ah, okay, okay.
So good morning, everybody. This is the second meeting we have this year on topological effects. So this is something very attractive these days. So the directors of this meeting are professors Carl Rizegis, Jaroslav, Daniel Loss, and Alan McDonald. I understand that Alan and Daniel will be here next week. So those guys are the ones responsible for putting together this very nice program, who attracted you all to Natal in the first place. I'm sure you will have a very good time here. You will probably enjoy very much the invited lectures and also the discussions which will follow the lectures as well. So it's a big pleasure to welcome you all on behalf of the organizers and of the staff of the IEP, and I wish you all a very successful meeting. So Jaroslav, I give, oh, Gerrit.
Okay, thank you very much. First, for the organizers and, of course, the gracious host of this great center here in the beautiful city. So let's just start with medias res. I would like to talk a little bit about YIG. And I think YIG is a very crucial material for the first part of this workshop. So I thought I'd give some introductory remarks and discuss some aspects of what I've been interested in or involved in personally in recent years. First of all, I would like to introduce the town where I'm coming from. This is Sendai in the north of Japan. It has a population which is quite similar to Natal, I think, and I guess maybe the universities of the same size. There's one big difference. I think there is much better skiing in Sendai than in Natal, but I think there are no buggy rides in Natal, so I think things are honestly distributed. Okay, so this is a topic of my talk. Just first talk a little bit about YIG, and then give you some examples of the games you can play with this magnificent material. Oh, now we have a problem. Support, please. No, that's not a good idea. Or you mean just to test it also? That might be okay. Nope. So the first time I met YIG, I was quite scared. So that's the title. Who's afraid of YIG? Because beauty is in the eyes of the beholder, right? Here you see YIG YIG in its complete beauty, and it's quite complex. I'd like to say it is really a monster, at least for someone who is used to simple elementary ferromagnets like copper or iron or something. What you see here are the yellow spheres are the yttrium ions, which are pretty big. They take a lot of space. And then you see these octaheders and tetraheders, which are formed from oxygen ions. And in each of these is one iron atom. Yes, 80 atoms in the unit cell and 20 magnetic moments. So YIG is about as old as myself. It was discovered in 1956, when I was born as well, by some French people. But it was the Bellabs who realized how useful it was, and they get loads of patents quickly after that. What you see here is the world of science, where you just put in what articles had YIG in the subject, and you get this picture. So it was discovered in 1957, and then you see it goes up, and then it sort of saturates for a long time. In the 90s, there's some jump, and there are some different interpretations about that. But what is interesting is that here in 2011, something happens. And I think this was the fault of my colleague, A.G. Saito, who discovered that YIG is interesting for spintronics. And you see it really picks up here, and there is no saturation whatsoever. Okay, I should mention actually that I'm sort of carrying olds to Athens here, because the one who knows most about YIG is Professor Resende. I guess he did it already during his PhD thesis, so if anything is missing here, please ask him. So Feynman already knew about YIG. It was in 1964, but he claims that YIG is not a ferrimagnet, but a ferromagnet, because yttrium supposedly has a lot of spin-orbit interaction. So either Mr. Feynman is joking, or he is mixing up yttrium with ytterbium. Because don't believe him, it is not a ferromagnet, it's a ferrimagnet. It's a very well-behaved ferrimagnet, because the iron shells are half-filled, so they have a large spin of 5½ and they are strongly antiferromagnetically coupled via superexchange the oxygens. So we have a nice collinear system here, but we have more of one spin than the other, and that's why there is a net magnetization in YIG. It is a ferromagnet. Now, it's a very convenient magnet. It has a high TC. It is a very good insulator. It has an excellent acoustic damping. And most important for us is the high magnetic quality factor of very low magnetization damping of the magnetization dynamics. So it has also interesting optical effects, but usually you have to do that by doping. So it is possible to calculate the band structure of YIG, which is actually not an easy task, because it's very big, very complex. And additionally, we know that conventional band structure calculations cannot really describe ionic insulators very well. The good news is that these band structure calculations, even in a local density approximation, give you a band gap. So in this respect, you can say it is really a band insulator. It's not a Mott insulator, for example. Now, by certain tricks, you can crick up your gap and get it closer to the experimental reality. And it's also possible to calculate different relevant properties like magnetization or spin mixing conductance, for example. Now, we are mainly interested in the low energy excitations of YIG of such a ferromagnet. Now, I thought most of you know that these excitations are spin waves or magnons, which are the solutions of the linearized Landau-Lifshitz equation. So the solutions are plane wave, dispersive plane waves, which have a certain wavelength, and an energy dispersion, which goes quadratically with the wave number. Now, it's possible to make wave packets out of these magnons, which correspond to dips in the magnetization, which move with the group velocity, and in this way can transport spin also in insulators. Now, the magnons obey Bose commutation rules, so their equilibrium distribution is given by this zero chemical potential Bose-Einstein distribution function, which at high temperature becomes a Rayleigh-Jeans distribution. Now, we are mainly interested in thin films, and in thin films we have to take into account the corrections to the dipolar interactions between the magnets, between the spins. Now, this is again a standard type of theory, so it is well known how the spin waves are modified by these classical magnetic dipolar interactions. And if you then solve these type of equations here, you can find a dispersion relation like that. Where you see here is the frequency, and this is the wave number. So these are very long waves in general, and you have three types of waves, which are called the forward-moving waves, the backward-moving volume waves, and we have also surface waves. And these surface waves have the interesting properties that they are chiral. They can only go in one direction. They are also referred to as Dayman-Eschbach modes. Now, this is a very small k, so we should always add the exchange term if we get further down into the Brillouin zone. Now, the spin waves can interact with other elementary interactions, and this is also, I think, quite old physics. Ask Professor Resende. But they can hybridize with the photons as well as with the phonons. So in this respect, they look quite similar, but there are differences. So the length scale here is quite different, and also the strength of the interaction is quite different. So the magnon-phonon interaction is really quite strong, and it is very close to the origin of the Brillouin zone. Now, in this regime here, we have the mixture between these states. There are no magnons, there are no phonons. There are mixed states called magnon polaritons. Now, usually people talk about the strong coupling when the broadening of these excitations is smaller than the splitting. So this is a strong coupling situation. Now, YIG has very little spin-orbit interaction. That means the magnon-phonon interaction also should be rather small. And indeed, if you plot it at this scale here, then it's hardly visible that there is indeed an anti-crossing also between the phonons and the magnons. But still, YIG is a very high quality, so it's even in this magnon-phonon system, we will see it is possible to get strong coupling between these two. Now, I was talking about ferromagnets, but YIG is a ferrimagnet, as we saw, right? So we have more up spins, up magnetic moments, and down magnetic moments. So what are the consequences of that? That means that we have now two different modes. There is a ferromagnetic mode, which precesses with a magnetic field. These are then the majority moments. But there are also, at higher energies, modes with the opposite spin, which almost do not feel the applied magnetic field, but mainly the exchange field of the majority ones, and they press in that one, which is then in opposite direction to what you would expect to the applied magnetic field. So this is the acoustic mode, and this is the optical mode, and the optical mode is much higher energy, and the splitting is the so-called exchange splitting. Of course, if you now make an antiferromagnet out of a ferrimagnet, then these two modes will become degenerate. And I think that we'll hear more about that during this workshop. Now here is an example of a typical ferrimagnet, which is magnetite. Now, the method of choice to measure these Magnon dispersions is inelastic neutron scattering, and you see here the experimental results. We see indeed acoustic magnons and optical magnons, and they are split by this exchange splitting here. So do you have to worry about it? Not actually, because if you look at room temperature, you will find out, you see that would be about here, and so the occupation of the optical magnons in magnetite is negligible, and we can really treat it like a ferromagnet. But how about YIG? It's a little bit more complicated, because YIG is a little bit more complicated. So if we want to understand what is happening here, we have to do a little bit more work. The model of choice to do that, to really understand the spin dynamics of YIG at finite temperatures, is based on the classical Heisenberg model. So this is a very good model here, because the spin is large, right? And it's a very isotropic material. So the Heisenberg model with the nearest neighbor, or eventually next nearest neighbors, is a very appropriate model here. So S is 5/2, the G factor is just 2. Now, then what we have to parameterize is the exchange coupling between one of the spins and the other spins. And this is, for example, a set of parameters, just 3 parameters, which turns out to be a very good description of YIG. Now, interestingly, we see that, that all 3 are negative. So basically, YIG should be frustrated. But because these here is really the largest one, the ground state configuration is still nicely collinear. Based on this Hamiltonian, we can derive an equation of motion, which, when linearized, gives you this spin wave distribution, this spin wave dispersion function. But we would like to do a little bit more. We also want to understand what is happening at finite temperatures and at finite damping. Now, the trick to do here has been first, I think, shown by Brown. It means you just connect the spins to a thermal bath, which gives you random disturbances of the spin configuration. And you can treat this, if you do this properly, according to Brown. You also have to take into account the damping, right? So this equation here now has this random, this stochastic magnetic field, and it has a damping parameter here. And this is the so-called Gilbert damping constant, which governs the magnetization dynamics of any ferromagnet. Now, these are fluctuating forces, and the damping are related by the fluctuation dissipation theorem, which in the classical limit looks like that. So the noise correlation is proportional to alpha and proportional to the temperature. So we get now an additional parameter, and this parameter is chosen a little bit larger than in the experiments for numerical convenience. Now, Joe Barker in our group in Sendai, he calculates by brute force the time-dependent LLG equation for each of these magnetic moments, always coupled to the other magnetic moments next to it. The result of it is a time series, the time dependence of the magnetization, from which you can calculate the time correlation function, and Fourier transform it into the spectral power function. And the plot here is a spectral power function in the reciprocal space as a function of frequency. Now, at low temperature, this noise is not so important, and what you then get is basically what you would get if you calculate the spin wave spectrum directly. And this is here the result for low temperatures for YIG. And it's indeed quite complicated, as you could expect. Now, the point is that for most experiments, we are really only interested in what happens very close to gamma, which is really this region around here. And also the dipolar corrections are only important very close to gamma here. We see here 2 sets of curves, the red ones, which are the acoustic ones, and the blue ones, which are the optic ones, which are the ones which precess in opposite direction. So what happens if we go to room temperature here? Now, Now, first of all, magnons start to interact because the amplitudes become larger and you get magnon-magnon interactions which become important, and in these calculations they are included to all orders. So all the parameters are exactly the same. What you see here only comes from the fact basically that you have larger fluctuations and magnon-magnon interactions. We see that these higher modes here, they really completely smeared out. There's almost no structure anymore. It's a large lifetime broadening. But fortunately, two modes are very stable against elevated temperatures, which are the fundamental ferromagnetic and the fundamental antiferromagnetic mode. So this is very convenient. And if you look at the spatial distribution, you see that these two are spatially separated from the floppy modes, other floppy modes, and that's why their lifetimes is pretty long, also at room temperature. So we have now two modes, and we also see, if we look at KBT, that these ones do play a role if you want to do things quantitatively. Yeah? Because these are flat bands to a large extent, so that means they are very susceptible to perturbations, they're to interactions. KBT is here, yeah, indeed, it's between 5 and 10 terahertz, but still, I guess, also these higher modes, they see the random motion of the other ones, and they're very susceptible to that. Yes? Okay, good. So, yeah, you can sort of test this by neutron. Yes? Yes, because these optical modes, they precess in the opposite direction and they suppress the spin-Seebeck effect, yes. Unfortunately, it is not sufficient to explain experiments. Yes, we could do that, but the agreement with experiments is not good. And the reason for that is that these calculations do not include transport. Right? This is basically sort of, if you would have no magnon transport, just look at the interface and you sample there the dynamics of the YIG. If you can do these calculations, but the suppression at higher temperatures is larger than that. So this is not the whole story for the spin-Seebeck effect. That's an important message, yes. Yes, yes, I think he is working on it, yeah. That's the next step. Now, this is also quite interesting, so you can compare these results with all neutron scattering experiments, and there's good agreement, which is not so surprising because the parameters have been fitted to these type of experiments. These experiments, they are already from the beginning of end of the 80s, something like that, very old experiments, but people are looking at it again because people are getting more interested in YIG. So I think we will probably get new insights there. I've seen some spectra, and I really don't understand what's happening there, so it's quite exciting. So what games can we play? Okay, the first one is you would like to put YIG into the microwave, right? And how are you doing that? So a good way to do that is to make use of cavities. Cavities are basically boxes for microwaves with reflecting interfaces, and the microwaves itself, they become standing waves in these boxes, in these cavities. And you can put different type of samples in there, for example, thin films like that. And then this question is, how do you detect what's happening? Now, one way is to make little holes into these cavities, to couple in your microwaves and to see what's coming out. So you have then the reflection of microwaves and the transmission of microwaves, which can be observed. Another way is try to observe it electrically by making use of the spin Hall effect with platinum contacts, for example. Now, I've shown you this picture before. If you look at bulk systems, we have the anti-crossing between the photons and the magnons. And this strong coupling regime can be detected by seeing splittings of the FMR absorption peaks, for example, like indicated here. So you can also do this by looking at the transmission of such a one-dimensional cavity like here. And these are calculational results which show indeed you have here, so what you see here is a magnetic field, and with the magnetic field you're shifting your excitations through one of these cavity modes, and you see this splittings here, which are a direct indication of this strong coupling regime. And this is not only for the Kittel mode, which means where all the spins are together, but we can also see that the spin wave modes, higher standing spin wave modes in the films can be detected as well. Now this was 2014. Here you see some nice experiments, which is a collaboration of the Manitoba and München group. And here you see the microwave spectra of a thin film in a cavity, and here you see the spin pumping results, and both are quite are sort of nicely correlated, and we can indeed see the strong coupling of the fundamental mode, but also of higher spin wave modes in these systems. Now you can also play other games with these cavities. Here, for example, this is a spherical cavities, and we have now not films, but spheres in this cavity. These type of experiments have also been carried out by several people. Now this is just a theoretical calculation where we show what is the microwave scattering of such a cavity as a function of the detuning between these two spheres. So you can have a little bit higher field here than here and see what happens. So now you can look at the scattering with and without this cavity, without this conducting sphere around it. And there's a big difference between these two. Without, you see just as a function of this detuning, the resonances of the two individual spheres, and nothing happens here at the origin. So these two are basically non-interacting. If you switch on the cavity, however, you see a strong anti-crossing here, a strong splitting. And we can understand this in terms of simple molecular orbital theory. Each of these magnons is a hydrogen atom. If you bring them together, they form bonding and anti-bonding orbitals, which then react differently with the microwaves. One of these modes is dark, is optically not known, and the other one is bright. So this is really sort of a chemical bond, a magnetic molecule, which only exists because you have the cavity. The microwaves here are the glues which sort of bind these things together. So this is, I guess, quite cute. Okay, next I would like to discuss experiments and theories where YIG interacts with light. Let's take with the first one, and this is a new technique which has been developed only in recent years, in which you do pump and probe experiments of thin films of YIG. So an experiment consists of a focused laser which hits your YIG, right, and sort of heats it up or excites it at the center, and then something will happen in time, right? And you can measure that by a probe beam in which you very quickly scan the whole film and see what is the magnetic response. So it's like throwing a stone into a pond, and you see then that the excitation goes like spheres, propagates outside. And one of these experiments from, this is Ogawa from RIKEN, it is really spectral like that. So this is really where the stone hit the water, and you see it's still oscillating there a bit. But you also see that some things go. So spin waves are propagating radially, and there is some very interesting structure in these spin waves. Now actually, the physics here is not new at all, because it turns out that what is important here are the phonons, and the coupling between phonons and magnons has been known for a long time. So we know what the Hamiltonian is, and we know how to solve the dynamics of such a Hamiltonian. And you can then calculate, say, the magnetic response as a Green's function in time and space, as a function of the excitation, which in this case would be more or less focused at the origin. Now, these calculations were carried out by Ka Shen in the Delft group, and these are the numerical results for two different time delays, 3 and 6 nanoseconds, and you can compare experiments and theory, and it agrees nicely to with each other. So what is happening here? So let's have a look again at the 6 nanosecond delay. So at t equals 0, we excite at the center, and we look what happens after 6 nanoseconds. So we see there are two rings here, right? And these rings, as I said, they are related to the magnons and the phonons. Now, how does it work? First of all, we can calculate what the velocity is, right? We know how far this ring, the radius of the ring, and so we know what the velocity is, and we know the time, so we know the velocity. And it turns out that these velocities we see, they are exactly the sound velocity of the phonons. And there are two phonons, the optical ones and the longitudinal ones. Now we can also look at these wave packets here, and we see that there is a certain wavelength. And this wavelength is short for the inner one, for the slower, for the slower modes, and it's larger here, the wavelength for the faster modes. Now the conclusion is that these two modes are related, and this is also, we can correlate this here with the crossing of the magnons and the phonons and this dispersion. And the conclusion you have also from the symmetry, you see there are different symmetries here, that the fast ones are related to the longitudinal phonons, to the mixture here of the longitudinal phonons with the magnons, and the slower ones are the transverse ones. Yes? That is because the k here is very, very small. It becomes parabolic at larger k, but you can, on this scale, it's not so important. This is for a thin film, indeed, but it's a pretty thick, thin film. So. There are actually, so if you look, I'm sort of simplifying things a little bit, but it's in the calculations, this is taken into account, but for the argument, this is sufficient. Because it's still basically what is important here is the crossing here. Now, what is now important? What gives this length scale here? And this has to do with the pulse you're hitting. If you have if the pulse, the optical pulse, is very broad, then in K space you excite only magnons with very long wavelengths. These experiments, which had been done before by Sato, did not populate these mixed states here at all, and you don't see them. So the intensity of these two rings depends strongly on how you focus your laser, how you excite the material. So now we can test this theory by applying a magnetic field which shifts the magnons relative to the phonons. And what you see here is then, okay, the velocity should be the same, but we see that the wavelength should be different. And also the intensity ratio between these two should also be different, because this one here is now almost not excited anymore. And exactly that is seen in experiment and theory, where here the difference is the applied magnetic field. You see here the intensities differ, and we also see that the wavelength here of the rings differ as well, just as we see in the experiment. Yes? Yes. So I think you really have to look at the matrix elements and the symmetry of this transverse motion and the magnetic motion. And there are selection rules which show that if you are in the crystal directions, it can only interact with the transverse ones. If you want to get interaction with the longitudinal ones, you have to go somewhere in between. It's maximum half there. This also this is okay. So the polarization here is unimportant. You can do these experiments for right and left polarized light, and you see results exactly the same. So what happens here is you are heating the sample in the center, so you're exciting the phonons, and these phonons, they propagate, and during this propagation, due to this mixing, they pick up the magnetic signal. Yes. Yeah, good question. Now this is then sort of, you can sort of go continue and do more of this, and this is these are results by Hashimoto from Sendai. So he measures again as a function of space and time the response due to a focused laser excitation, and then he Fourier transforms everything into Fourier space, and then you get these type of experiments. And what you see here, for example, you see you do not see only this Magnon phonon, which is this strong peak here, but you also see smaller signals, which are due to the phonons, but also due to the magnons. This one here, for example, which goes down in frequency with wavelength, is the backward moving volume mode of YIG. Here you see also one goes up, which would be the Damon-Eschbach surface mode. And you can sort of analyze all of that. You get lots of information. And Hashimoto-san calls this spin wave tomography as a new technique. Okay, other interesting games you can play with light have been carried out by Tokyo group, Yale, and Cambridge group. Now this is a technique which is very useful in biology and so forth and so forth. It's what you're doing here is a evanescent coupling of spheres to light, and this light is carried can be carried different ways. In this case, it's just an optical fiber. So this is a single mode optical fiber, and you can put in light from here, and you can put also light from there, and sort of look at the transmitted light. Right. So now the point is that you can now look at the inelastically scattered component of the light, because the light is coupled here dispersively to the sphere, and there it can interact with the magnons, and it can excite magnons, or it can absorb magnons and change this frequency. So this is basically the Brillouin zone light scattering. It's a form of Raman scattering. Now the interesting thing is here that if you feed in the light and look at the inelastic scattering in pore 2, then you get the red curve. If you do the same, feeding in light from the other side and look at the transmission, then you get the blue curve. So there is some strong asymmetry in the system, and this can be understood, and I try to explain this. So here I try to make a sketch on what is happening here. So this is the light which comes in, right, which is single mode light. It can have two types of polarizations. And this light is not really confined to the fiber, it leaks a little bit out. It has some evanescent amplitudes, and the evanescent amplitudes overlap here with the normal modes of light in this sphere, in this YIG sphere. Now, by tuning the frequencies and wavelengths, then it's possible to excite selectively those modes in the sphere which have the largest overlap. These are the so-called whispering gallery modes, and I've indicated one of these here in this sphere. So these are states with a large momentum, large angular momentum with a short wavelength, and they are sort of localized at the spheres around here. So you can couple this to this these waves, and there they can interact with the magnetic system. Now, an important point is that these TE and TM modes, they are degenerate in the fiber. They are not degenerate in the sphere. They are actually split. This is called geometrical birefringence. Now, we are now interested in the scattering of the light of these whispering gallery modes with the magnons. And this is actually quite efficient because these whispering gallery modes can go along for a long time before they are channeled out again by the evanescent coupling. And so you would like to look for these type of inelastic scattering ones where you have Magnon absorption, which are the anti-Stokes, and Magnon generation, which are the Stokes lines. The frequency goes up or goes down. In order to get the scattering, we must sort of have some resonance condition, and you have to obey some selection rules. For example, it turns out that if you come in with the TE mode, it cannot be scattered by magnons into another TE mode. It can only be scattered into the TM mode by selection rules. So this is a triple resonance condition which you have to fulfill. And this is a picture I got from Yale, where you're coming in here with a TM mode and you're going out with the TE mode, which is redshifted, so it has excited a magnon. And this can all be measured in great detail, although it seems to be not so trivial. Now, what types of magnons are important? It turns out there are two families of magnons which are important, which are those which are close to the fundamental Kittel mode. The Kittel mode is the one where all the spins, they move coherently with each other. The other important mode is now the whispering gallery modes for the magnons. And these are actually the Damon-Eschbach modes, what we know from the films, but then in a spherical geometry. Okay? Now, if we now look at the Kittel mode, or the ones which are close to it, they have, compared to the light, very low energy, and also compared to the Y wavelength, very low wavelength. So the momentum and energy conservation rules dictate that you cannot have reflection in this case. You have to look in transmission. So inelastic transmission, and if you're coming in with a TE, and we have to go to a TM mode. Now the TM mode is now shifted by the linear birefringence, and this gives you the asymmetry which we saw before. In this case, we are only in the regimes of the proper magnons by magnon emission and not in magnon absorption. So you see only the Stokes, or the Stokes ones are much stronger than the anti-Stokes in these type of experiments. Now this is experiments which have been done, but it's also interesting now to look what happens with these Damon-Eschbach modes. They have also very low energy compared to the light, but they have a large angular momentum. And again, in the parameter regime of interest, this angular momentum is large enough to backscatter the light. I don't want to go into too much details, but we knew that these Damon-Eschbach modes, they can only go in one direction. There is no mode which goes in the opposite direction. And depending on the specific configuration, we have a selectivity here of really 100%. There is a symmetry rule which forbids, in this configuration, the anti-Stokes, while the Stokes are allowed. Now, experiments are going on to look at that, and San Sharma, he is finishing the article here. I would like to make some advertisement for a workshop which discusses the interaction of YIG in cavities, in optical or microwave cavities. We call it spin cavitronics. Actually it was Heido Sinova who sort of forced us to give this workshop, but I think it might be quite nice. So how much time do I have, Mr. Chairman? 15 or 5? Okay, so YIG is also interesting for electronics because it has been shown by A.G. Saito and collaborators that you can excite the magnetization electrically, right, by putting on metallic contacts and then especially platinum. So I would like to focus here on basically this time of configuration. And the point is that, so let's start first with this one here. This was an experiment already a few years ago in which it was shown that the electrical resistance of a platinum film can be modulated by the magnetization direction of a magnetic substrate. Now this was quite surprising in the beginning because YIG is really a very good insulator. So the electrons here are not supposed to see any magnetism at all. Now the experiment here consists simply you drive a current through this and you look at the voltage difference here in the same probe. Now these experiments here, I guess first carried out by Cornelissen and a little bit later by Gönnenwein, this is now a sort of a non-local SMR spin Hall magnetoresistance where we have two contacts. Now they drive a current through the platinum here and they look at the voltage at the contact which is at a distance. So the fact that you see a voltage here might already be surprising, but it can be understood. So because we have these two different types of processes, one is the spin transfer torque, which means that if you absorb a spin current at an interface, you can absorb them and excite the ferromagnet. And the other process, the reciprocal process, is the spin pumping, which says that if you have magnetization dynamics at a metallic contact, it generates a spin current. Now, the spin current here, which comes in, can be detected, can be generated, or is usually generated by the spin Hall effect, and the detection is by the inverse spin Hall effect. So these contacts usually are heavy metals such as platinum. Now, actually, there have been several experiments here. Ones in the right ones are on the lateral type of transverse configuration, and there are also a couple of experiments on the longitudinal one. Now, how can we understand this? So again, we have excitation of the magnet at one point and we detect it on the other. And the only way how these two can communicate with each other is via the magnons, right? Then the question is what is in what regime are we and how should we understand that? And I think there Rembert Duine has I think really made a good argument and convinced me how to think about these things. What we have to do is to consider that the magnons on these really large samples, they do interact. They interact with impurities, they interact with phonons, they interact with other magnons, for example. And all these interactions, there are two types of scattering processes. Those ones which are magnon conserving and those which are magnon non-conserving, right? Now the magnon non-conserving ones in a material like YIG, they must be weak, even at room temperature, because we know that the magnetization damping in these materials is very, very small. And magnetization damping means you're losing magnetizations, you are annihilating magnons. Now, if we assume that this one here is weak, it's the weakest scale in the problem, then the problem can become rather easy. And let's see how this works. We mentioned already, magnons itself are bosons, right? So they are distributed according to Bose-Einstein distribution function. But magnons, like as phonons, they are pure energy, so the chemical potential at equilibrium is 0. However, excited states of magnons, they can have a distribution function we do not really know, in principle. But we can argue, or Rembert argued in the following way. Assume that we excite the magnon systems electrically or optically in some way. Then the first, at least at elevated temperatures, very important scattering process is Magnon-Magnon interaction. And the Magnon-Magnon interaction, they sort of thermalize the Magnon distribution function, right? So that means in a very, very fast, if you excite the system very fast, you get an excited and a higher temperature. That means if we go here from a distribution function times density of state, which is this black curve, and you heat it up, then you get this red curve. But then we have to take into account all the other scattering processes, right? And we just said that Magnon non-conserving processes are weak. So the number of Magnons now in relaxation should not change. But you do have strong Magnon-phonon scattering, for example. And the Magnons are hot, the phonons are cold. So these Magnon-phonon scattering processes, they draw energy out of your distribution function. And the question is how you describe that. You cannot do this with zero chemical potential because you cannot get the energy out of the system just by that. But what you can do, and this is actually the same what you do in metals, you can introduce a non-equilibrium chemical potential mu. And via this mu, by introducing this mu, you can withdraw energy out of your distribution function and still keep the total number of Magnons the same. And then you see that starting from this red one, and we let energy go out of the system to the lattice, we are coming to this green one by allowing this additional degree of freedom of the chemical potential. We see that in this way, the distribution now becomes more or less focused at the band edge and becomes larger and larger. So if you allow to continue that, then at some point, you get, of course, what is called Magnon-Bose condensation. And I think Beta and Jaroslav will talk a little bit of what can be expected then. Now, the point is now that if we now assume that indeed the Magnons are not allowed to have different temperatures than the phonons, and the only degree of freedom we have then to describe the transport is this chemical potential, and we assume that there is diffuse transport, then this chemical potential at its position dependence is the only parameter in the system. And then it's quite straightforward to show, going to the Boltzmann equation, that we can reduce the Boltzmann equation to this simple diffusion equation with one parameter, which is the Magnon spin flip length, the Magnon spin coherence length. And this simple equation more or less perfectly agrees with experiments. And the interesting thing is that the relaxation length scale here is in the tenths of micrometers. Yes? Then things is getting much more complicated, yes. But at this point, at room temperature, there is no need to do that. Everything works perfectly well with this one parameter. So I would like to add that people did this type of experiments on metals for decades already. Huh? So there you have two ferromagnetic contacts, and you have a normal metal substrate, and you get exactly the same equation to describe spin transport. But in metals, a spin flip length of 20-30 micron has never been realized. And so the fact that it has such a long spin coherence length is directly related to the weak small Gilbert damping in YIG. In principle, yes, but nothing has been seen in this respect. So I think a complete theory of transport of magnons, say on the Boltzmann limit, was taking all these complications into account, at this point does not exist. I think you tell me. you have worked on that, right? So, but yeah. Okay, so yeah. Yes. Yeah, so that is something which puzzled me for quite some time, but it's basically very easy. It's just an efficient way of describing a distribution function we do not know exactly. If you recall what we do in metals, in normal metals, if we inject spins, then it's now fully accepted that these spins can be described by a spin accumulation. Spin accumulation is basically the difference between the chemical potential of spin up and spin down. Now now yeah, here's not really up and down here. You have just an, yes. At interfaces, these two match, has also been discussed in great detail by Jaroslav. But it's, yeah, at this point, it's simply a very efficient way to describe a non-equilibrium distribution function. And sort of you can try to do this in a more detailed way, in a more microscopic way. But presently, at room temperature, there doesn't seem to be a need to do that. At low temperatures, all these arguments which I showed, all these Rembart's arguments, they don't hold anymore. At low temperature, things get much more complicated. And yeah. Yes. Yeah, so at least the Groningen people, I don't think, at low temperature things get strange. At room temperature, I think everything seems to be perfectly well. Yeah, yeah. Okay. At very low distance, they have some fitting problems. That's true. Yes. So they cannot. There's some. If you have some additional fitting parameters, might help. Yeah. Yeah, but okay. But all these parameters are not too well known. So basically, you're coming down to fitting parameters, right? It is, in principle, should be possible. Yes, you can. Yes, yes. And that's basically whether you say you go to low temperatures at large distances or you go at very slow distances at room temperature. This is quite similar. Right? Yeah, it's the same. If you have the same distance and you go to lower temperatures, you will see this new physics as well at large distances. Okay. Yeah. Okay. Right. Is this published or unpublished? Okay. Yes, true. I agree. Okay, good. Yeah. So what's next? Yeah. So you could speculate what happens here in the experiments of Olivier Klein. Which, when exciting with a higher current, he suddenly sees large non-linearities. Then you might ask the question, okay, is this now related to the fact that the chemical potential becomes large enough that it comes close to the band gap and gives some condensation phenomena or not? But I'll leave this work to the experts. I just want to show this figure. I think my time is up. I will then skip the work of YIG and the spin-Seebeck effect. Just want to show that people are now already able to generate millivolts with spin-Seebeck effect, which really might become useful. And I would have discussed about these anomalies in the spin-Seebeck effect, in which actually beta played a big role in understanding it. So I'm skipping this stuff here. Let's see what is. This is a sort of overview, right? I think I mentioned most things. And these are my collaborators in recent years. And I would like to thank you very much for your attention.
Questions?